Hi, everyone. Thank you for having me here. My name is Igor Andreoni. I'm a Neil Gehrels Fellow at University of Maryland and at NASA Goddard. And I would like to tell you a bit about the discovery of AT2022 CMC, which we interpret as a jetty TDE, and we found it in an optical survey. Just to kind of see, I will be bouncing a lot from optical to X-ray and radio, so I added some cartoon pictures that hopefully will help guide the eye during the various plots. And in general, if I find a first author of a paper I'm citing who's present in the room, you will see the color in yellow, and I hope I will not have forgotten, I have not forgotten anyone. Another important question to keep in mind is JACE 1644 plus 67 still the coolest jetty TDE out there? I will leave it to you to determine. But that's definitely a great starting point for the talk I would like to present you. So what happened for the discovery of this jetty TDE is that a gamma ray burst was found by the Swift satellite. An alert was released to let the community know that something was happening. Unfortunately, people recognized straight away that this was an object of interest, so they could truly throw all the resources they had available, and this is how this great multi-wavelength data set was built. The gamma ray emission that you can see here up top is constituted by this very long-lasting and highly variable light curve. In the optical, basically there was non-detection. What you can see here is basically there was galaxy that just was found as an excess, with an excess compared to the background. There was, however, a hint of a flare in the infrared. But this is probably okay because the circumstellar density of the around the source was measured to be really high. So that's not a big surprise. So in the optical, however, now we have new tools for which we can run large surveys and go look for either your favorite type of transient, but even they open a new space for discovery. And I would like to just, before getting to the science, just remind everyone this tends to be a big data problem. I've just written here some of the numbers that kind of describe the data releases of ZTF. We're talking about mining millions of imagings as hundreds of billions of light curves or light curve detections. And what you see here in this video appearing are supernovae that are found by ZTF, or at least detected by ZTF, and then identified as such. So it's a very powerful tool to have a survey with a wide field of view that can scan the sky over and over again, allowing us to study the sky in the time domain. I'm personally interested quite a lot in multi-messenger sources. So I like to look for fast transients that could be either afterglows or kilonova perhaps. Maybe one will be found tonight. We don't know. We're searching hard. I can guarantee that. What we did here is just create a framework for discovery. So going from alerts that are generated and released publicly, at least for 50% of the survey, we do force photometry, some various selection criteria in various steps. I can talk as much as you want about it, but in short, we want to find rapidly evolving transients as soon as possible, or at least within 24 hours from the first detection. If we're lucky enough, which should be enough to then trigger follow-up observations on candidates we're fairly confident about, and then truly then have discovery and science happen. As a matter of fact, we managed to make kind of routine to find afterglows from gamma ray bursts, or even orphan afterglows sometimes. So we started as part of the ZTF collaboration in particular, and also this has become routine for other projects, just to kind of reverse the process. We're not waiting anymore for a gamma ray burst to happen. We can find a transient in the optical and then look back, see if there was a gamma ray burst that happened coincident with it, possibly associated, or the lack thereof, which I think is a very intriguing field of research nowadays. And sometimes things fall in our bucket, and we simply have no idea what they could be. And I think if you are, for example, a gamma ray data analysis expert, you may not see straight away what's exciting for an optical astronomer, or vice versa. But I think even optical astronomers don't see necessarily a very exciting transient here. But that's the plot that was sent on Slack to us by the automatic pipeline. Basically what we observed, here you have time on the x-axis from 0 to 3 days from the first detection, and just basically optical luminosity magnitudes on the y-axis. We found this transient that increased its luminosity by about a couple of magnitudes in one night, seemed to be declining fast, and then kind of plateaued after a day. So it's been at that time a long time that the camera was offline, so it was particularly easy for some young postdoc to feel excited about even something like this, although there was no host galaxy. So what you see here is an archival image in which the transient is located at the center of. So I heard quite remarkable methods to find TDEs based on host galaxy properties. I just remind everyone, you may not be seeing at all the host galaxy of a very exciting transient. So what happened then is that we released immediately the fact that there was a possibly fast transient at that location, and DJ Pasham at MIT just pointed nicer at it, and a very, very bright source was revealed. Then turned out to be very luminous also in the radio. And in the optical, something truly odd was observed. The third data point that maybe was a plateau actually was maybe a bit of a fluke. The transients kept going dimmer and dimmer very rapidly for a few more days. So this plot is very rich. It's probably a bit hard to read. So I encourage you just follow the red Gaussian processes that just guide the eye. You have this initial peak that lasts in rest frame after you know what the redshift is for just a couple of days, and then this turns into a plateau. Something quite peculiar is not just the shape overall of the light curve, which is probably unprecedented as far as I know, but it's also that the initial fast transient was very red in color, and the plateau was very blue in color, very hot. And that's typically not how nature works. Typically it goes from hot to cold, not the other way around. So this is probably due to multiple components playing together. So once again, as a reminder, big surveys are great to find the transients you're looking for and classify population of them, and also to find some gems. And that's why I put Fritz Zwickie's picture there. I think he would be proud that in an instrument named after him, both of these aspects can be developed, can be looked into. In addition, some of our collaborators also got some polarization data. I think these were taken pretty much when the fast component turned into the slower component. Long story short, polarization data indicate that it's consistent with 0. I encourage you to read Alex Chicota's paper if you would like to know more. Spectroscopy, especially for optical astronomy, is truly one of the best methods that we have to classify the sources, to find the distances, work out the energetics. Is vital. That's why we want to do things in real time. We acquired a bunch of spectra, thanks to which, especially thanks to the VLT spectrum, we managed to get a hold for the first time in this campaign of the redshift, which is about 1.2. It's a cosmological source, and maybe that's why we don't see the host. It's just extremely distant. And overall, we do not see any of the broad features that were shown in spectra also during this conference many, many times. No hydrogen, no helium, not the broad features you would expect from a TDE. What you have is a pretty much smooth, featureless continuum that is, well, kind of red at the beginning, which you don't quite see here, but definitely turns bluer at later stages. What about the X-rays and sub-millimeter once you aggregate all the data that you acquire, in this case in the first months of observations? You see a transient that, once again, once you know the distance, is as luminous as the two other better-known jetted TDE. And that's what kind of gave it away to us, was not necessarily the smoking gun. It's hard to have a smoking gun in this case, but that helped us interpret this source as a jetted TDE. And you can see how distinguished those light curves are in luminosity. Here, the isotropic equivalent luminosity is more than like 5×10⁻47 ergs per second, and truly separates them from the other type, the most standard gamma ray burst afterglows that here are represented with the light gray lines on the left plot. On the right-hand plot, you can see the radio light curve at radio sub-millimeter, more around 100 gigahertz. And you can tell that 22 CMC truly stands out. Is, I think, as far as I know, the brightest, the most luminous sub-millimeter transient at this phase known so far. But please let me know if that's not the case. And very recently, a paper was published by Terane Eftekhari et al. That show that a drop in the X-ray light curve was eventually found. And one of the reasons why this is interesting and important is that it truly helps in, with some not so easy method to quantify, at least estimate an upper limit on the mass of the supermassive black hole. Once again, under the hypothesis that this is indeed a jetted TDE. And the constraints that they found are quite remarkable, about at most 10 to the 5th solar masses. So I encourage you also to give a look at this very recent paper if you want to learn more about their interpretation. The radio light curve that I've learned is still alive. It's still out there. You can still observe 22 CMC with your radio telescopes. In addition to the kind of slower evolution that might be expected from this type of sources, and most type of relativistic transient, also shows some very short time scale variability. That's around 15 gigahertz. And in addition, some people, for example, Yuhan Yao, who's present here, Wen Bin, and others have collected all the data together from the radio to the hard X-rays and tried to model the whole SED. The models that you see plotted in these figures come from the work done by DJ Pasham and led by the MIT team. And something you can notice also is how the overall SED truly differentiate 22 CMC from blazars. Although quite often you can see an association in conversation about jetted TDEs between this class of transients and blazars. And for our paper in particular, the lead theorist was Wen Bin, to whom I'm really grateful for the exceptional work that he has done. And this is a bit, what I think is a useful cartoon picture to understand a bit how we believe, what we believe happened in the context of this transient. So there is a jet which kind of easily explains our observation of an optical transient that is red and fast, basically like an afterglow. Although I'm still not clear to me why we see it on the rise. This doesn't happen, at least not often, when we find afterglows associated to standard gamma ray burst. So this jet and their forward and reverse shocks are likely responsible for this early optical component and probably also from the radio millimeter and the X-ray emission. However, the late time blue thermal component that can be actually modeled pretty well with a black body is probably due to an outflow which here in this cartoon picture is represented by the blue patch on the left side around the black hole. But there are some people who believe that also other models could explain the observations. I see Brian maybe not too convinced about his own paper, but...
Which aspect? I believe this is an afterglow. Whether I think it's a supernova, how it changed.
So there are some far-fetched theories, but that are... no, it's... that I think actually is very important.
Idea, I forgot.
It is possible, because models might fit the data, that this is not a TDE, but could be some engine-powered supernova, because the world is full of space oddities. And again, that's kind of a mission, I think, for us to truly unveil a large population and see what that more accurate statistical analysis can tell us about the property of the population as a whole, besides all the individual transients that we find. So what about the host galaxy? Pretty much nothing. That's kind of the summary. In our paper, we could derive some upper limits from archival images, which are not too bad for optical transient astronomy, but were definitely not enough to find the host. Our HST observations, even at late time, more than 3 months after discovery, were still let's say, polluted by the transient itself, that was still too bright. We were not expecting this long-lasting plateau when we proposed for HST DDT time. And I don't think this is necessarily the plateau that Stuart was talking about for TDEs. This is still very luminous. However, Erika Hammerstein is now leading a paper on the long-term optical and infrared light curve, and maybe that a bit more will be revealed there. Just a quick note about the Lorentz factor. I saw in different papers quite a broad range of values. I think if we say it's somewhere between 10 to 80, 100, that's kind of the ballpark where pretty much everyone agrees. So from a few dozens, probably. That's the bulk Lorentz factor of this event. Rates are quite important here. So with a bunch of caveats that we have discussed actually with some of you during the past break, the rate for jetty TDEs that were inferred from the X-rays, so based on the detection rate from SWIFT, and the detection rate of 8022 CMC-like transient in ZTF, they agree pretty well. Now, it's very hard to tell how complete we were in ZTF, or even for the SWIFT team for deriving these rates. But as far as we can tell, the two rates kind of agree to each other. And the two things that one probably can derive from this good match is, one, that probably the denser circumstellar material, like for J1644, maybe being so dense is not that common. Otherwise, probably we just wouldn't have almost any in the optical, though with 1 ± -1, that's a pretty far-fetched argument. And I think the more important point here is that about 1% of TDEs actually show jets that we can observe in the optical, after you normalize for the geometry with your favorite assumption on the viewing angle. And it's already been talked about, a possible connection between jetty TDEs and this new class of luminous featureless TDEs that are now found quite regularly in optical surveys. So this is actually something I noticed while Erika was giving a talk at the AAS. She showed a plot of the life curve of one of these luminous featureless TDEs, and I'm like, I saw that somewhere. It was spot on, like the blue component, the kind of the plateau phase of 22 CMC. And if you go back to in the literature, you can see that this is also similar to what was observed during the follow-up of previous JET-TDE candidates. This is just a hunch, but maybe it's enough, I think, to prompt some more investigation about this connection. And something quite nice is that quite naively, you just plot up the peak luminosity of all type of TDEs, and you just mark with a different color the one that are featureless in their spectra. You can see they all fall at very high luminosity regime and spot on where we observe the peak of this slow evolving component for 22 CMC. So I will just leave you with a quick summary. So in general, the systematic exploration of the transient sky in your favorite band, in our case in the optical, truly can reveal some gems and allow you to do a work that can reveal the rate and probably something more of the source you're studying, besides just jumping around and just hoping to look for everything that explodes in a random way. And that also can enable rapid follow-up, which truly was key, I think, to collect the data sets that can allow us to interpret an object like this, like 22 CMC. We interpret it as a JET-TDE, but we still haven't seen the host galaxy. Again, we don't know if it's located at the center of the host. So hopefully the Hubble proposal that is now under review will be accepted. In case someone is in the TAC, please consider that. And yeah, the prospect of finding more of this type of trains in the Rubio Observatory, I think, is quite intriguing. And I will stop here. Thank you very much.
Okay. Any questions?
Thanks, Igor, for this nice review. You say it's still on the plateau, or is it, is it declining? Because if the original plateau, you saw it from ground-based telescopes, right? Can you still say if it's there, or is the HST data showing some decline? So
I probably should have used different words than plateau. I apologize for that. In our discovery image, so the first 3 days, it looked like it was, the light curve was already becoming flat, but that was not eventually the case.
The blue plateau later.
But then there was this blue plateau a few days later. Mm-hmm. The HST images indicate that the luminosity was not much lower than this plateau. I think maybe I don't know if Erica is around and remember on top of her head. I'm really sorry to put you in the spot. Do you remember on top of your head the late time photometry for Hubble, like 3-4 months after discovery? Okay, so the plateau actually started turning quite significantly. Okay. Thank you.
Thanks.
Well, okay, while Yair is at the mic, can you guys give us a 10-second summary of the status of neutron star black hole EM counterpart searches?
Igor is much more hardcore than me.
Yeah. So, quick summary. There was this event a few days ago, labeled S240422ED, so happened the 22nd.
Matzo-ball merger, which I should say was Italian idea, not.
You can put that as your favorite event on the board if you'd like.
Can I? Thank you. So this event was of interest because it's like a neutron star black hole merger, in which the mass of the black hole is small enough so that it's very likely that some ejecta are present, so a bright electromagnetic counterpart should be there, given the parameter estimation that the LIGO folks did. In addition, Virgo is back online, and I think not many people have appreciated the importance of it. So the sky map, now the 90% localization region is a bit less than 300 square degrees, which is manageable as opposed to like all sky type of sky map you have with just 2 detectors. So all of this is very good. What's not very good is that it is happening right behind our own galaxy. So you have a lot of stars, dust, and extinction between you and the merger, but we're doing what we can to go deep and red to find transients. The other not very good thing is that there is full moon these days. So it's harder to reach the depth that is required to find kilonovae. A whole bunch of teams are looking at the region of interest. I'm one of the PIs for the DECAM follow-up with the dark energy camera. We have observed for 3 nights in a row, and we're scanning for candidates and publishing them as soon as we find anything possibly of interest, or at least that we believe is likely extragalactic. And the whole community is doing that, vetting candidates, doing follow-up. And I think, has anything happened while I was talking?
No. No, the short answer is there's no obvious candidates.
Yes.
I will just add, if you want to follow along, there are 2 places you can look. One is treasuremap.space. You can see where everyone is looking. And the other is you can go to a service called Hermes, Hermes, and you search for the gravitational wave name. It'll give you all the messages that people are posting about all the candidates, all the follow-up, everything. More than you want to know.
Well, thank you guys. I did not mean to put you on the spot, but I appreciate that.
Pleasure.
Okay, so now continuing on the tidal disruption theme.
Yeah. But at least people will forgive me now if they saw me on the laptop these days. This is why.
Can you go back to the SED plot? So first, let me say I would not so easily throw blazars out for the similarity. Yeah. I mean, it's true we don't really see thermal emission for most cases, but there are a couple of sources that, that we do see accretion disk emission. So it still looks pretty blazary to me. And also that connects with the featureless TDEs people have been talking about. This is something we see in blazars all the time. Just the jet continuum swaps out all the emission lines. My question about this was more of the timing of the data you have there. Does the color coding correspond? Does it not exactly, the lines? Are the data simultaneous? That's the first question. And when are the X-ray observations with respect to
so this is not my paper, but the first author is in the room. I'm sorry putting you guys on the spot.
No worries. So the main point that we have here is that in New Star and NICER, we see a break in the X-ray spectrum. So the label is 7.8 days, 17.6, and 36.2 days after the optical discovery. And those UV and optical SEDs are the simultaneous with the X-ray SED. And we're saying that because we see it's actually not a good, because we're, I was plotting PyCharm 2023 models to say that it doesn't match the X-ray SED because we see a break there. And because of that, we don't think synchrotron self-Compton is the mechanism that is producing the X-ray, which is what it is in blazars.
Okay, but the radio is in the different times.
The radio is spanning the time, so the redder it is, the later it is. So the radio is covering the X-ray observations. Yeah, but it's like, I think it's from 5 days to 40 days. Yeah.
Thank you.
Thank you, Johan.
So I have a question that might be more for the theory modelers, but it's sort of striking that in 1644 and MC, the radio doesn't look like an on-axis afterglow, right? And by contrast, take long GRBs, selected based on a jet pointing towards us. They all show declining afterglow light curves. So what is different about these TD selected events that somehow we're finding them either a little bit off axis, or maybe it's not really a single energy injection, maybe it really is the continuous energy injection from the central engine?
So my opinion in the context of J1644 differs a little bit from the Basel, from Paz and Tatsuya, was that we think the jet had a lot of angular structure, that there's a lot of variability in the X-rays, which could be consistent with some kind of jet which is initially not aligned with the viewer's axis, but then perhaps due to, in other words, if the disk is misaligned with the spin of the black hole, it may take some time for the jet to align, and during that process, you may end up creating a very structured jet that wouldn't be present in a system where the spin is aligned with the disk. So I would argue that the jet may be influenced by precession or other things and give it more angular structure. So there could actually be more energy slightly out of your line of sight than along the line of sight.
So just two quick comments. One, in GRBs in the radio, actually we do see peaks at slightly later times. So the radio is not declining from the beginning typically. It's peaking at around 2 weeks or so for an average GRB afterglow. And this is basically when nu M crosses the observed band. And the other thing is that the lower Lorentz factor that we likely have here compared to the GRB case means that deceleration can be quite late, and even late enough to actually mess up this typical light curve that we see in the GRB case. So that's another potential difference.
I will argue that there's a break at the early part of J1644 that I think is deceleration.
Yes, I agree that the early break in 1644 is likely deceleration.
Okay. Any questions for Igor, actually? All right, well, let's thank Igor again for a great talk and everybody else in the session.